our second example, n plus 5 over n squared plus 6. The sum is that n goes from 1 to infinity. So limit comparison test. Now, how do we know limit comparison test? Because this is polynomial divided by polynomial. Limit comparison test is just like this is what it eats for lunch. So limit comparison test, we're going to compare with, and the series you compare with is you take dominant term over dominant term. You may ignore the coefficients if there were any. This is 1 over n. That's the harmonic series. The harmonic series diverges. It's a p series with p equal to 1. This diverges because it's the harmonic series. So if these agree, then this then this series will also diverge. A good question is, what happens, okay, if this works out to be finite and positive? What if it's not finite and positive? Well, first off, how could it be neither finite nor positive? Well, one result is if this works out to be infinity. If this works out to be infinity, then what this means is you should not have been using this test in the first place. You were using the wrong tool for this job. It was not the right series, it was not the right test to use on this series. If this works out to be 0, that tells you you should not have been using the limit comparison test in the first place. All right? So we're going to compare this with here. So we have limit comparison test. Let's start with the limit. Unknown over known. And a little algebra here. Multiply by reciprocal. So this is the limit as n goes to infinity of n squared plus 5 over, this is n squared plus 6. And this is our useful result. If the degrees are equal, the limit is the fraction of coefficients. This is 1 over 1, which is finite and positive. Therefore, they agree. Therefore, always intersperse this result. Therefore, they agree. And therefore, they agree with what? They agree this diverges. The series diverges. All right? It turns out this sum is infinity. That's not obvious, but that's what actually happens here. All right. Next example. This is not a polynomial this time. The polynomials, you should be sort of getting the hang of it. Let's see what happens if it's not a polynomial. Well, how would that work out? Here's my little example here. This is example number 3. And we have the third root of n over n plus 4. And we're going to compare. Again, this is an algebraic function over an algebraic function. So we can use the limit comparison test. It seems like a good candidate. And we're going to compare with, change to exponential form. Change this to exponential form. This is n to the 1/3 over n to the 1st. Simplify that result. When you divide the bases, you subtract the exponents. And so this is 1 over n to the 2/3. 1 minus 1/3 is 2/3. This is a p series with p between 0 and 1. This is 0 less than equal to p is less than or equal to 1. So this diverges. All right, so now let's see what happens here. Again, use exponential form, not the radical form. So we have n to the 1/3 over n plus 4 over 1 over n to the 2/3. When you multiply the bases, add the exponents. So this is n to the 1/3, n plus 4, times n to the 2/3, When you multiply the bases, add the exponents. This is the limit as n goes to infinity. This is n to the first over n plus 4. Our useful result says if the if the degrees are equal, then the limit is the fraction of coefficients. Therefore, this is, they agree, because this is finite and positive, and if they agree, therefore they both diverge. The series diverges. All right? So I think after you work through several of those examples, the limit comparison test works out to be very straightforward and not particularly challenging in its computation and in the actual work you're doing.